Hi all of you. We're going to start with the refraction of light through a plane surface. Okay, the first answer, getting back to work straight away, is about refraction. Now, if someone asks me, what is refraction? It is nothing but a phenomenon of the bending of a ray of light when it enters from one medium to another medium after striking the surface. So when a ray of light strikes the surface and enters into the other medium, there is a deviation, there is a bending of ray of light, and that is called refraction. If you talk about the three diagrams or the three conditions for refraction, the first one, when the ray of light enters into a denser medium from a rarer medium. So, rarer to denser medium, let's see what happens. Second condition, when the ray of light goes from a denser medium to a rarer medium. So, denser to rarer. And the third condition is when the ray of light falls normal to the surface, perpendicular to the surface. So we're going to look forward to the diagrams of these three conditions. The first one, ray of light coming from rarer, example air, to a denser medium, example water or a glass. Come on, when the ray of light falls from a rarer medium to a denser medium, at this point of incidence, we'll draw a normal angle of incidence. Out here, the ray of light falls from a denser medium to a rarer medium. Angle of incidence and the point of incidence. And in the third criteria, the ray of light falls normal to the surface, perpendicular to the surface. Here, angle of incidence is 0. Let's see what happens, guys. Okay, in the first condition, rarer to denser, the bending is towards the normal. Right, so this is gonna bend towards the normal, and this is gonna be R, the angle of refraction. In the second case, the bending is gonna be away from the normal. This is gonna be R. And in the third case, there is no bending, it goes straight downwards, where R is also equal to 0. So these are the three diagrammatic representations. If you happen to write conditions over it, first one, can I say rarer to denser, bending is towards the normal? The second condition, obviously by a mere look, angle I is greater than angle R. So angle of incidence is greater than the angle of refraction. And definitely the denser medium has a lot of atoms and particles, as a result of which the speed reduces. So there is an obstacle, there is hindrance out here. So the speed of light decreases. Even there is a small effect in the brightness. However, 3 points suffice to the answer. Out here again, the bending is away from the normal. Second pointer, the speed increases. And third, the angle of incidence is less than the angle of refraction. Out here, angle of incidence is equal to the angle of refraction. There is no deviation, no bending. And third, talking about the speed, definitely it depends. If it goes from a rarer to denser medium, the speed slightly reduces. And from a denser to rarer, the speed slightly increases. So third point, I can say it depends that light is entering from which medium to which medium. So these are the three conditions as my first answer with the definition of refraction. Right. Second part or the second answer for y'all. It is about the laws of reflection, the laws of refraction. The first law, I can say the angle of incidence, the incident ray, let's take the same example. The incident ray, the refracted ray and the normal, they lie in the same plane at that point of incidence. Now we have three-dimensional geometry. This is one of the planes. This can be considered as the second plane, and the ground can be considered as the third plane. So if the angle of incidence is in one of the plane, then obviously you can't have angle of refraction in the other plane. They have to be in the same plane. Yeah, the same plane. So I can say the first law, incident ray, the refracted ray, and the normal at the point of incidence where they meet. They meet at the point of incidence. They lie in the same plane. And the second point, we have something called as refractive index represented by mu. Okay, mu 1, 2, it means that the ray of light is coming from the first medium and it is entering into the second medium. It goes direct. And the formula is, it is equal to sine of angle of incidence to sine of angle of refraction. We call this as Snell's law. Now what does Snell's law state? The Snell's law states that the refractive index is equal to the ratio of the sine of angle of incidence to the sine of angle of refraction. And the way it is pronounced is backwards. We call it as the refractive index of second medium with respect to the first medium. That's how we pronounce. Yes. So this is Snell's law, and these are my two laws of refraction. However, we have a formula as well to continue for this. Mu 1, 2 can be written as mu 2 upon mu 1, or it can also be written as V1 upon V2. Now this is very crucial, very crucial. If you observe carefully, mu, the formula is reversed. It is refractive index of second medium with respect to the refractive index of first medium. So it is not mu 1 upon mu 2. It is mu 2 upon mu 1. It goes reciprocated. However, if you talk about V1 and V2, it goes straight. Mu 1, 2 is velocity of light in the first medium upon velocity of light in the second medium. So if I'm talking about a formula in terms of mu, it's reversed, but in terms of velocity, it is straight. Let me give you another example. The ray of light is coming from air to glass. So air to glass. The formula will be mu of glass upon mu of air. Another formula is velocity of light in air goes straight upon velocity of light in glass. So if I'm talking about the formula in terms of velocity, it goes straight. Velocity of light in air to the velocity of light in glass. That's the ratio. But if you're talking in terms of mu, it is the other way around. So from this part, I can claim that the mu and the velocity are inversely proportional. Check. This is mu 2, but this is V1. We have V2 out here. So I can say the refractive index is inversely proportional to the velocity of light in a medium. Remember that. So from here, can we state that red colored light has the maximum velocity and the violet colored light has the minimum velocity. So if red has the maximum velocity, its refractive index is minimum. Violet has the minimum velocity, its refractive index is maximum. Simple language, violet is going to bend more bending because it is more affected by the refractive index, by the material, medium, the nature. Red colored light, super fast, no time for turning. I don't want to bend. I'm not gonna fall down, right? So max velocity, it is least affected by the refractive index. All right, guys. So we have done couple of concepts. Go through them and we shall take few more, guys. Talking about the cause of refraction. Now, just a simple thing. Why does refraction happen? Two reasons. First, when the ray of light enters from air to glass, taking an example, in air or in vacuum, the speed of all the colors of Vibgyor, that is right from red to violet, right? The speed of all the colors in air or vacuum of light remains the same. But once the white light or the sunlight enters into the other medium, the speed changes. Red colored light travels the fastest and the violet travels the slowest. So I can say, because of the change in the speed, one tries to travel faster, bend less. Other tries to travel slow, bend more. That's the reason why there is a refraction. There is a change in the direction of light. Another cause of refraction is the change in the medium. Whenever there is a change in the medium, there is a change in the refractive index. Yeah, the refractive index changes. The density of the medium changes, as a result of which the refraction occurs. So two reasons, simple, change in the speed, and second, change in the density, the medium, the material, the nature, the refractive index. All right, let's study about the next answer, guys. The cause of refraction. Oh, I'm sorry, that is done, right? The factors that affect, okay, the factors which affect refraction. Okay, now I think refraction means the refractive index, obviously. Come on, the factors which affect the refractive index, that's more appropriate. Now, the first factor is the nature, yep, or the material medium. The second factor is the conditions like temperature, and the third factor is wavelength or color. So there are the three factors, these are the three factors which affect the refractive index, right? Let's start about the nature or the material medium. Can I say, as the density increases, the refractive index also increases. And if the refractive index increases, the thickness, the resistance, the number of atoms of that medium increases. And if there is an increase in the number of atoms and particles, guys, obviously the speed decreases. So can I say, increase in the mu refractive index, decrease in the speed of light. Right, guys. And few minutes back, I guess I've done this with you all. I can say, if I talk about the nature, the red light travels the fastest and the violet light travels the slowest. So I can say that mu refractive index for red color is the least. It's and the refractive index for the violet color is the max. Temperature. If the temperature increases, the molecules, the particles of that medium, they are in agitation. They start moving. Or temperature increase. They start moving. They start running. As a result of which, the speed of light, the path has increased. The path has widened. The area has increased. The space has been made because the particles are running. So they are away from each other. So can I say the speed increases? And if the speed increases, refractive index decreases. So can I say temperature increases, speed increases, guys. And if speed increases, the refractive index decreases. Lambda or color. The red color has the least mu, least refractive index, and red color has a wavelength of 8,000 angstrom units. Violet color has the maximum refractive index and it has approximately wavelength of 4,000 angstrom unit. So can I say, more the wavelength, more the speed. More the speed, less is the refractive index. So I can say that color wavelength is inversely proportional to refractive index, temperature is inversely proportional to refractive index. Right, so these were the factors affecting refractive index. The fourth one, you can talk about the principle of reversibility. Reversibility. Now that's very simple. Whenever I switch on a torch, let's say a torch, or consider one ray of light. It goes from a rarer medium to denser medium. Example, it goes from air to glass. Right with this? Now obviously, rarer to denser bending will be towards the normal. Fine. If I happen to write this in terms of mu, the refractive index, it is mu air to glass, and according to the formula, it is mu of glass upon mu of air. Equation number 1. Now what I do is, I trace back the same path of light in the opposite direction. So what I'm trying to do is, this light, the source, the torch, I put it out here, I place it out here. And what I do is, I exactly retrace the light, the path of light. When I retrace it exact in the same, on the same of what it was, that is overlap, even from here, it goes back into the same path. It exactly follows the reverse direction, the reverse path. And this is called principle of reversibility. Now, in the second condition, the ray of light is moving from a denser to rarer medium. So it is moving from glass to air, and the formula will be mu of air upon mu of glass. Equation 2. Multiply both of them. So mu air to glass multiplied by mu glass to air, it is mu g upon mu a into mu a upon mu g. That cancels out. So I get mu ag into mu ga, isn't it equal to 1? And get that down, guys, get that down. So mu refractive index is 1 upon refractive index air to glass. This is the connection. Okay. My fifth answer for y'all would be the conditions for no deviation. Two simple conditions. Condition number 1. Whenever the ray of light enters from one medium to another medium in which the refractive index of both the media are the same. Didn't get it. Example. When the ray of light is entering from air to vacuum, can I say in both of them, the refractive index is approximately 1 only. So can I say if the refractive indices of both the media are almost the same, the bending does not take place. The ray of light prefers traveling straight. And the second condition is when the ray of light falls perpendicular to the surface, where I is equal to R is equal to 0, no bending takes place again. So two conditions. First, refractive indices are almost the same, and second, a ray of light falling normal to the surface. So go through this. There are a couple of question answers more to the crash course part of A of this chapter, A part only, right? Go through this. The next answer is about the lateral displacement, then the thickness and the glass slab experiment in the A part. So again, if I talk about the glass slab experiment and the lateral displacement, yeah, it goes this way. Let's say that there is a glass slab out here, okay, and if the ray of light falls, from a rarer to denser medium, this is going to be the angle of incidence, the point of incidence, and the normal. Bending is going to be towards the normal. Okay, again, if I happen to draw a normal, this is angle of refraction, angle of refraction. Again, now the ray of light goes from a denser to a rarer medium, the bending is going to be away from the normal. Okay, if this glass slab would not have been there, can I say this ray of light would have gone straight? There would not have been any deviation. So this distance between the emergent ray, this is the incident ray, and this is the refracted ray. So I can say the distance between the emergent ray and the direction of incident ray, when traced forwards is called lateral. Lateral means sideways displacement. Lateral displacement. Okay, so it is the distance between the actual emergent ray and the direction of the incident ray if that ray would not have gone forward. Right with this, guys? Perfect. And then, of course, this is called angle of emergence. Now, this lateral displacement depends upon three factors. So, the factors affecting lateral displacement are, one of them is the angle of incidence. The second is the thickness of the glass slab or thickness of the medium. And the third one, it is the refractive index, which is mu. So these are the three factors which affect the lateral displacement. Now let's quickly study about the angle of incidence. Simple. You take a glass slab. If this is angle of incidence, it's huge in my example. This is the bending and another bending. Now observe this. If I trace it forwards, this is the lateral displacement. With the same thickness of the glass slab, if the angle of incidence is less, bending, check the amount of lateral displacement. It's less. So can I say more the angle of incidence, more is the lateral displacement, less the angle of incidence, less is the bending, less is the lateral displacement, less is the distance between the emergent ray and the direction of the incident ray. Alright, so I can say directly proportional or inversely proportional? Directly proportional. Second, thickness. If I talk about more the thickness and if I talk about lesser the thickness, okay, more the thickness, let's start. I'm keeping the angle of incidence the same in both the cases. No changes in the angle of incidence. Come on, yeah. Bend, bend. Bend, bend. So I can say from here, more the thickness, more is the deviation, more is the bending. Less the thickness, less is the deviation, less is the lateral displacement. So I can say it is directly proportional. And of course, it depends upon the refractive index also. If the refractive index is high, the medium is denser, it has more particles, it has more density, there is going to be a lot of hindrance, lot of bending. And I can say if bending is more, come on, lateral displacement is more. So I can say more the refractive index, more is the lateral displacement. Simple. Okay. Talking about the last portion, the last part of the A section of this chapter, the thickness of the glass slab. So let's say there is a thick glass slab out here with me. All right. And there is a screen out here. This is the screen. At the bottom of the glass slab, we have a silver colored surface acting like a mirror. And at the bottom, we have an opaque surface like a wood. So I can say the bottom portion acts as a plane mirror. And this is nothing but a glass slab. Okay. If I talk about a slit and I talk about a source of light, fine. The ray of light falls on the glass slab. At this, 4% approximately is reflected. We call it as a partial reflection. And majority 96% is refracted. So this is approximately 96% of light which is refracted, enters into the other medium. bending towards the normal from rarer to denser. Yep. At this point, we make a normal. And because of the mirror, the plane mirror, it suffers a complete reflection, a total reflection. So the ray of light is reflected and some portion of the light still remains inside and the majority of the portion goes outside. So approximately 96% goes outside and 4% travels inside. And this keeps on going on. There is a partial reflection and a partial refraction. Partial reflection and a partial refraction. It goes on. And I can say that the intensity, the brightness keeps on decreasing. If I happen to trace all these rays backwards, this is your image I1. This is your image I2. And this is going to be your image I3 and so on. And I can say I2 is the brightest of all images. I2 is the brightest because check, it's 96% of energy, of light energy. I can say I2, that is the second image, is the brightest. Why is it the brightest? Because the ray of light suffers an internal reflection, a strong internal reflection from the silver surface of a plane mirror. And because of that, it suffers a strong internal reflection. Thus, the second image is stated to be the brightest of all the images. Alright guys, with this, we complete our crash course portion part. I've tried to cover as many concepts as possible of A. B, C and D shall go very fast. Proceeding with the B part, guys. Talking about a prism. Okay, in a prism, we directly jump to the diagram of a prism. Alright, so for a given prism, this is said to be the angle of the prism, the angle A of the prism. Talking about a ray of light which is incident at some angle. This is the incident ray, the point of incidence, the normal, the angle of incidence. Fine. Whenever the light ray enters from a rarer to a denser medium, bending is towards the normal. The refracted ray, you call this as R1. Here also I'm going to draw a normal. And this is going to be the emergent ray. So 3 rays. So I can say this is the angle of emergence. This is R2. Alright. Out here, if this ray would not have been deviated, if this incident ray would not have been diverted, it would have gone straight. And this ray, what happens is, basically, this ray just happens to go straight, but because of refraction, it bends and it falls down. This ray bends from here and it falls down. That means if you trace this back, isn't this the amount of deviation delta which has taken place? Obviously, because look at this. The incident ray bend and go down. That means the bending which has taken place is at an angle which I have marked out here. That is called the deviation. The difference in the angle between the emergent ray and the incident ray. Right. This is called the base of the prism. Now always remember, a prism has 5 surfaces, out of which 2 rectangular surfaces are inclined and the base is a rectangular surface. And the frontier and the posterior surface, the front and the back, are the triangular surfaces. So this is something like a prism. Alright, out here I want you to remember a few formulae. The first one, I plus E is equals to A plus delta. The second formula is, however, just these formulas I want you to by heart because they will be useful in the numericals point of view. Fine. Second formula, it is R1 plus R2 is equals to A. This is said to be delta 1, the first deviation, and this is said to be delta 2, the second deviation. I is equal to delta 1 plus R1, vertically opposite angles, and E is equals to delta 2 plus R2. When you add both of them, I get this. I plus E is equal to A plus delta. And delta 1 plus delta 2, the sum of two remote interior angles is the exterior angle property. So delta is equals to delta 1 plus delta 2. So what we have done is, first thing, just check this one. I is equal to R1 plus delta 1. E, vertically opposite angles, is R2 plus delta 2. When you add both of them, I plus E is equal to delta 1 plus delta 2, which is delta, R1 plus R2, which is A. That's how I get it. Fine. Out here, we're talking now about the conditions for deviation, right? The conditions. The first condition. Or you can also talk about the factors which affect the deviation. The factors affecting deviation of the ray of light. Delta stands for deviation, or you can write the entire word. The first factor is the refractive index. Second factor is the angle of prism. Third factor is the color or the wavelength of light. And the fourth factor which affects the angle of deviation is the angle of incidence. Now that's an important one. You talk about refractive index. More the refractive index, more is the density. More the density, I can say the bending will be more, the deviation will be more. So more the refractive index, more is the bending, more is the deviation. That's the first one for you. Talking about the second one, the angle of prism. Observe, if the angle of prism increases, can I say the prism is becoming thicker? If the prism becomes thicker, the number of atoms and molecules keep on increasing. And if the molecules or atoms increase, the crowding increases. Crowding increases, the hindrance, the obstacles increase. As a result of which the deviation increases. So I can say more the angle of incidence, more the angle of prism, angle of incidence comes later. More is the bending and more is the deviation. Okay, the third part, talking about lambda. Now, if you talk about red colored light, the red one, I can say the red colored light has a lambda, lambda of 8000 angstrom unit, and a violet colored light has a lambda of 4000 angstrom units. So can I say more the wavelength, faster is the light. Speed, this is slow as compared to the red light. So I can say if red light travels the fastest, it has more wavelength, the bending will be less. So I will say the deviation for the red light is minimum and the deviation for the violet light is maximum, right? So factors affecting the deviation, red light deviates the least, violet deviates the most. And the last portion, it is the angle of incidence. Now that's important, that's crucial. Remember one thing, with angle of incidence, the angle of deviation changes in a peculiar manner. First, check. Now this is angle of deviation and this is angle of incidence. Look what happens. As the angle of incidence increases initially, the angle of deviation keeps on decreasing. At a particular point, we reach a minimum deviation for a particular angle of incidence. I am repeating. As we keep on increasing the angle of incidence, the angle of deviation decreases. It reaches a minimum value at a particular angle of incidence. And thereby, if you further increase the angle of incidence, the angle of deviation also keeps on, it keeps on increasing. So I can say this point is called delta mean and this point is a point where you get the angle of minimum deviation. So guys, when do we get angle of minimum deviation? Come on. As the angle of incidence increases, the angle of deviation decreases, it reaches a minimum value. After that, when you further down the line increase the angle of incidence, the angle of deviation does not decrease. I'm sorry, it increases. So it is a multiple behavior, a mixed nature, right? And at this point, guys, at this point, that's called angle of minimum deviation. We observe certain things. What do we observe? First, we observe that the refracted ray is parallel to the base of the prism. That's what we observe. First observation. The refracted ray is parallel to the base of the prism. Second, what do we observe? We observe that angle of incidence is equal to the angle of emergence. Come on. Angle of incidence and angle of emergence are the same. That's what we observe. And third, what we observe is this R1 is equal to R2. And that's the three observations. These are the three observations for angle of minimum deviation, delta. So this was my B part for the chapter for you all. Okay, so in the B part crash course, all I can take is the prism, the factors, yeah, and the angle of minimum deviation.